All right, let's jump right in. Naming chemical compounds. They can feel like you're trying to learn a secret code, right? You see all these formulas, but the names seem to follow a set of rules that are just impossible to figure out. Well, guess what? Today, we are going to crack that code.
I mean, seriously, what's the deal here? How come one name is loaded with prefixes like de and mono, but the other one is so straightforward? It looks totally random. But I promise you, by the end of this, you're going to see the simple, beautiful logic behind all this seeming chaos.
And that's really the secret sauce. You can forget about trying to memorize hundreds of different rules and exceptions. The entire system, all of chemical naming, it all hinges on you being able to answer just one single question right at the start.
This is it. This is the master key that unlocks the whole thing. Once you get this down, you'll know exactly which set of rules to use every single time. You ready?
This is the question. That is all you need to ask yourself. Before you even think about writing a prefix or balancing a charge, you have to decide, is the thing I'm looking at ionic or molecular? Everything, and I mean everything, follows from this one decision.
So let's break that down. What's an ionic compound? It's really simple. It's just a partnership between a metal and a nonmetal. Just picture your periodic table. You're grabbing an element from the metal side and pairing it up with one from the nonmetal side. That's it.
And a molecular compound? Well, that's a team made up of only nonmetals. Two or more elements from that corner of the periodic table joined together. Oh, and you might hear these called covalent compounds too. Don't let that throw you. They're the exact same thing.
Okay, let's put them side by side because this is the whole game right here. You look at a formula, you find the elements on the periodic table, and you ask the question, metal plus a nonmetal. You're going down the ionic path. Two nonmetals, that's the molecular path. Two different paths, two totally different sets of rules.
All right, so let's say you ask the question and the answer is ionic. Let's head down that path first. When you're dealing with a metal and a nonmetal, the name of the game is all about balancing charges. The whole goal is to make the compound electrically neutral.
Let's use aluminum oxide as our example. First step, find their charges. Aluminum likes to have a 3+ charge and oxygen a 2- charge. See? Not balanced. So we need to find a common multiple, which is 6. That means we need 2 aluminums to get to a +6 and 3 oxygens to get to a -6. And that gives us our formula, Al2O3. A lot of people call this the crisscross method, where you just swap the numbers. It's a fantastic shortcut. Okay, now for our first little wrinkle, the transition metals. Those elements in the big middle block of the periodic table? They can have more than one possible charge. So how do we know which one it is? Easy. The name tells us with a Roman numeral. If you see iron 3 oxide, that's the chemistry's way of saying, hey, use the iron with the 3+ charge. And here's the second special case, polyatomic ions. Now, these look scary, but they're not. They're just little groups of atoms, like phosphate here, that act like a single unit with one overall charge. If you need more than one of them to balance things out, you just put them in parentheses before you add the subscript. It's like putting a fence around them to keep the group together. So let's do a super quick recap of the ionic path. It is all about making the total charge 0. Remember, the nonmetal's name gets an "-ide" ending. And you just got to use Roman numerals and parentheses for those special cases. Got it? Awesome.
Now let's back up and check out that other path. What if your compound is made of 2 nonmetals? Well, you can just forget everything we just talked about. Forget about charges. This path is so much simpler. It's all about counting, and we do that with prefixes. This table right here, this is going to be your best friend on the molecular path. You really, really need to know these. Mono is 1, di is 2, tri is 3. You get the idea. These little prefixes are going to do basically all the work for you. And this brings me to the single most important rule for this path. If you remember one thing, make it this. I'm going to say it again because it's that critical. For molecular or covalent compounds, you do not balance charges. Not at all. Ever. Just don't do it. Honestly, it's almost funny how simple this is compared to the ionic stuff. The name literally spells out the formula for you. Diphosphorus? Okay, di means 2, so that's 2 phosphorus atoms, P2. Pentoxide? Pent means 5, so that's 5 oxygen atoms, O5. Slap them together, P2O5, you're done. No charges, no crisscrossing, no drama. Okay, to really prove that we've mastered this, we need to be able to go in reverse. We need to go from the formula back to the name. So let's put this new skill to the test and work backwards. All right, here we go. I'm going to throw a beast up here.
Cu3PO42. That looks pretty complicated, right? But it's not. We just have to apply our system, and that starts with our one key question. So what do we ask first? You know it. Is it ionic or is it molecular? Do we have a metal in there? Let's look at what we've got. We have Cu, which is copper, and that polyatomic ion, phosphate.
Yep, copper is definitely a metal. So, boom, right away, we know exactly which path we're on. We're on the ionic path, and that means we need to start thinking about charges, not prefixes.
Okay, next step. Copper is a transition metal. That should set off a little alarm in your head. It means we're probably going to need a Roman numeral in the name. But what is its charge? The formula itself holds the clue.
And this is where that crisscross trick is so cool, because we can use it in reverse. Look at the subscript on the outside of the phosphate parentheses. It's a 2, right? Well, that 2 was originally the charge on the copper, which means the charge is 2+, so the name has to be copper 2-phosphate. See? The formula told us everything we needed to know.
So, there you have it. What started out looking like a confusing, chaotic mess of rules is actually a really logical and predictable language. Once you know to ask that one key question, you know how to speak it.
You came in thinking chemical naming was some kind of impossible maze with no map, but it turns out the whole thing opens up with a single key. Is it ionic or molecular? Now that you have that key, it kind of makes you wonder, doesn't it? What other intimidating parts of science are just a secret language waiting for you to learn the key?